Oumuamua, the first confirmed interstellar object to traverse our solar system, has captivated astronomers since its discovery in 2017. Recent studies in 2025, including analyses of its trajectory and composition, have provided compelling evidence that resolves key enigmas surrounding its origin and behavior. This development not only clarifies Oumuamua's nature as a fragment from a distant planetary system, but also enhances our understanding of interstellar space dynamics. To appreciate the significance of these findings, consider the broader context of interstellar exploration. Discovered by the Pan-STARRS telescope in Hawaii on October 19, 2017, Oumuamua, meaning scout or messenger from afar in Hawaiian, entered our solar system at a hyperbolic velocity of about 26 kilometers per second, 16 miles per second, far exceeding typical solar system speeds. Its path indicated an origin beyond our stellar neighborhood, possibly from a star system light years away. For an audience that witnessed the Apollo missions and the Space Shuttle era, this echoes the excitement of early space race discoveries, but on a cosmic scale, reminding us how far astrophysics has evolved since the Cold War competitions between NASA and Soviet programs. In this video, we'll examine Oumuamua's anomalous acceleration without a visible comet tail, defying initial expectations. Previous theories, from exotic alien probes proposed by Harvard astrophysicist Avi Loeb, to natural explanations like hydrogen icebergs or nitrogen fragments. New evidence from 2025 studies, including simulations of giant planet systems ejecting such objects, and refined models of outgassing mechanisms, implications for future interstellar object detections, and broader lessons in space physics. Drawing on official NASA data, peer-reviewed journals like the monthly notices of the Royal Astronomical Society, and analyses from experts such as Avi Loeb and teams at UC Berkeley, this examination relies on verified sources to provide a thorough, evidence-based perspective. The discovery of Oumuamua marked a pivotal moment in interstellar astronomy, expanding our view of objects traversing the vast expanses of space beyond our solar system. To fully grasp its significance, we must trace the historical context of interstellar object detections, beginning with early theoretical predictions and building to recent confirmations. Astronomers have long hypothesized the existence of interstellar objects, bodies ejected from distant star systems and wandering through the galaxy. This concept gained traction during the Cold War space race, when advancements in telescope technology, such as those used in NASA's early planetary surveys, allowed for deeper observations of the cosmos. For instance, in the 1960s, as audiences watched the Apollo missions unfold, physicists like Freeman Dyson proposed that rogue planets or comets could be flung into interstellar space by gravitational interactions in forming solar systems. This built on Einstein's general relativity, which underpins our understanding of orbital dynamics and hyperbolic trajectories, paths unbound by a star's gravity. A key touchpoint came in 1984 with the theoretical work of Alan Jackson and Stephen Desch, who modeled how giant planets, like Jupiter, could eject icy fragments during system formation, potentially sending them on interstellar journeys at velocities exceeding 20 kilometers per second, 12 miles per second. These ideas were refined in the 1990s through simulations using data from the Hubble Space Telescope, revealing that such ejections could occur frequently in young star systems. The timeline of Oumuamua's discovery began on October 19, 2017, when Robert Warwick, using the Pan-STARRS-1 telescope at Haleakala Observatory in Hawaii, identified an object moving at 26 kilometers per second, 16 miles per second, relative to the Sun. Initially designated as 1I 2017 U1, it was the first confirmed interstellar visitor, with a reddish hue and elongated shape estimated at 100 to 1,000 meters, 328 to 3,280 feet long, based on light curve analysis from telescopes like the Very Large Telescope in Chile. Unlike typical comets, it showed no outgassing tail, yet exhibited non-gravitational acceleration of about 5 times 10 to the power of -6 meters per second squared, 1.6 times 10 to the power of -5 feet per second squared, as measured by NASA's Jet Propulsion Laboratory ephemeris data. Subsequent detections include 2I Borisov in 2019, a comet-like object with clear hydrogen cyanide emissions, and most recently, 3I Atlas on July 1, 2025, discovered by the Asteroid Terrestrial Impact Last Alert System Atlas Survey. According to NASA science reports published in August 2025, 3I Atlas shares similarities with Oumuamua, including a hyperbolic orbit and anomalous brightness variations, prompting renewed analysis of interstellar physics. For our audience, many of whom followed the Space Shuttle program's launches in the 1980s and 1990s, Oumuamua evokes the thrill of those eras, when space exploration shifted from lunar landings to probing the outer solar system with Voyager probes. It connects lived experiences of witnessing humanity's first steps into space with today's data-driven insights into the galaxy's nomadic wanderers, emphasizing how ground-based observatories continue to reveal the universe's hidden mechanics. Drawing from peer-reviewed sources, such as the Astrophysical Journal and NASA technical assessments, this background sets the stage for examining Oumuamua's peculiarities in greater depth. With the background established, let us delve into the technical aspects of Oumuamua's characteristics and the initial theories proposed to explain them. This section focuses on its anomalous behavior, inferred physical properties, and early interpretive models, drawing from astronomical data and simulations. First, consider Oumuamua's discovery and trajectory, which immediately set it apart in interstellar space studies. Detected on October 19, 2017, by the Pan-STARRS-1 telescope, the object exhibited a hyperbolic orbit with an eccentricity of 1.2, confirming its interstellar origin. Its inbound velocity was approximately 26 kilometers per second, 16 miles per second, suggesting it had traveled through space for millions of years before entering our solar system. Supporting facts include NASA's ephemeris calculations showed a perihelion distance of 0.25 astronomical units, AU, from the Sun on September 9, 2017. Photometric observations from the Hubble Space Telescope indicated a rotation period of about 8 hours. The object's brightness varied by a factor of 10, implying an elongated shape with an aspect ratio up to 10:1. Spectral analysis revealed a reddish color consistent with organic-rich surfaces exposed to cosmic rays, and no detectable coma or tail was observed, unlike typical comets, as reported in the Astrophysical Journal Letters in 2017. Next, the most puzzling feature was Oumuamua's non-gravitational acceleration, a deviation from a purely Keplerian orbit. Measurements from ground-based telescopes and the Gaia spacecraft quantified this acceleration at roughly 5 times 10 to the power of -6 meters per second squared, 1.6 times 10 to the power of -5 feet per second squared, directed away from the Sun. This implied an outgassing mechanism, yet infrared observations by the Spitzer Space Telescope in November 2017 detected no carbon dioxide, carbon monoxide, or water vapor emissions above limits of 10 to the power of 23 molecules per second. Key supporting details. The acceleration peaked post-perihelion, consistent with solar heating models. Tidal forces were ruled out due to the object's small size, estimated at 100 to 200 meters, 328 to 656 feet in length. Comparisons with solar system comets showed similar magnitudes, but required unseen volatiles. Dynamical simulations in a 2018 Nature Astronomy paper suggested thrust equivalent to 0.1% of the object's mass lost as gas, and the absence of a dust tail limited dust production to less than 2 kilograms per second, 4.4 pounds per second, per European Southern Observatory data. From an astrophysics perspective, these traits challenged conventional models. The high aspect ratio suggested fracture from a parent body, possibly via gravitational disruption in a distant system, but implied structural integrity under rotational stresses up to 10 to the 5 pascals, 14.5 pounds per square inch. Real-world implications include refining detection algorithms for future surveys like the Vera C. Rubin Observatory, which could identify dozens of interstellar objects annually. Early theories attempted to reconcile these observations. One natural explanation posited Oumuamua as a hydrogen iceberg, as proposed in a 2020 Astrophysical Journal Letters study by Daryl Seligman and Gregory Laughlin. Solar radiation could sublimate molecular hydrogen, providing thrust without detectable signatures, supported by formation models in giant molecular clouds where hydrogen freezes at 3 Kelvin, -454 degrees Fahrenheit. However, critics noted instability under interstellar radiation. Alternatively, a 2021 paper in the Journal of Geophysical Research, Planets, suggested a nitrogen ice fragment from a Pluto-like body ejected by impacts. Calculations showed nitrogen sublimation could match the acceleration, with a mass loss rate of 10 to the power of 4 kilograms, 22,046 pounds, over the flyby, and spectral matches to Triton's surface. Yet, the required parent body abundance raised questions about galactic distribution. A more exotic hypothesis came from Harvard physicist Avi Loeb in his 2018 paper and book, Extraterrestrial. Oumuamua's flat shape and acceleration might indicate an artificial probe, like a light sail propelled by radiation pressure. Supporting points included deviation from expected interstellar object populations, lack of cometary activity, and trajectory scouting the habitable zone. However, mainstream analyses, such as a 2019 Nature review, favored natural origins, citing statistical likelihood in a galaxy with 10 to the power of 11 stars. These perspectives highlight trade-offs in interstellar physics. Natural models require rare compositions, while artificial ones demand extraordinary evidence. As we transition, recent 2025 studies on similar objects like 3I/Atlas build on these foundations. Building on the foundational theories explored earlier, recent 2025 studies have provided fresh insights into Oumuamua's nature, shifting the discourse toward more robust natural explanations while acknowledging ongoing debates. This section analyzes these developments from multiple perspectives, including astrophysical modeling, comparative interstellar object studies, and broader implications for space exploration, incorporating expert viewpoints and trade-offs in interpretive frameworks. From an astrophysical perspective, the emphasis is on technical trade-offs in explaining Oumuamua's non-gravitational acceleration without invoking exotic mechanisms. A February 2025 study in the monthly notices of the Royal Astronomical Society by Ziling Zheng and Shilin Zhou simulated single giant planet systems around low-mass stars, 0.5 solar masses, demonstrating how gravitational perturbations could eject elongated, icy fragments with high eccentricities and small pericenters. Their models predict that such systems common in the galaxy could produce objects like Oumuamua with aspect ratios up to 10:1 and velocities of 20 to 30 kilometers per second, 12 to 19 miles per second. Pros include alignment with observed galactic distributions, where 10 to the power of 26 such objects may exist per cubic parsec. Cons involve the rarity of nitrogen or hydrogen compositions stable over interstellar distances, as radiation erosion could reduce mass by 90% over 10 to the power of 6 years per complementary simulations. Comparatively, the discovery of 3I Atlas on July 1, 2025 by the Atlas Survey offers a benchmark. Unlike Oumuamua, 3I Atlas exhibits clear cometary activity, releasing water vapor at rates of 10 to the 25 molecules per second, as observed by NASA's SWIFT telescope in August 2025, leading to a brightness increase of 2 magnitudes. This contrasts with Oumuamua's dust-limited outgassing, suggesting diverse formation pathways. 3I Atlas, likely from a water-rich exocomet belt, while Oumuamua may be a desiccated remnant. A September 2025 Space.com report posits Oumuamua as an exo-Pluto fragment, ejected from a dwarf planet analog, with pros in explaining its reddish hue via tholin formation under cosmic rays, but cons in requiring precise impact events for fragmentation. From an industry perspective, these findings set precedents for future detections, influencing observatory designs like the Vera C. Rubin Observatory, operational since January 2025, which could spot 15 to 70 interstellar objects annually. Long-term ROI includes enhanced planetary defense models. For instance, a November 2025 Science Alert study quantifies Earth's southern hemisphere at higher risk from interstellar impacts due to orbital inclinations, prompting investments in surveys costing $500 million, but yielding data for decades. Expert insights enrich this analysis, as Dr. Avi Loeb, Harvard astrophysicist, stated in a July 2025 Medium article. The arrival of 3I Atlas provides comparative data, challenging us to distinguish natural anomalies from potential artifacts. Conversely, Daryl Seligman, University of Chicago researcher, noted in a 2025 Planetary Society podcast, these objects teach us about planetesimal relics, broadly similar to solar system comets, refining our models of galactic chemistry. Finally, NASA's Karen Meach emphasized in a 2023 update revisited in 2025, studying Oumuamua's acceleration via hydrogen outgassing aligns with comet behavior, demystifying its path. These perspectives underscore the evolution in interstellar physics, balancing empirical data with interpretive caution, paving the way for future missions to intercept such visitors. Oumuamua as a silent voyager, a cosmic wanderer launched from a distant star system eons ago, hurtling through the cold void of interstellar space like a message in a bottle, cast into an endless ocean. Discovered in 2017 as it skimmed past our sun, this enigmatic object sparked a scientific odyssey that mirrors the epic quests of explorers from humanity's past. From the Viking longships navigating uncharted seas to the Apollo astronauts venturing to the moon, we've examined Oumuamua from multiple angles, piecing together its story like detectives reconstructing an ancient tale. Here's what stands out. Key finding 1. Oumuamua's anomalous acceleration, devoid of a visible comet tail, points to subtle outgassing from exotic ices like hydrogen or nitrogen, as evidenced by 2025 simulations in the monthly notices of the Royal Astronomical Society, which model mass loss rates of up to 10 to the 4th kilograms, 22,046 pounds, during solar flyby, explaining deviations of 5 times 10 to the power of -6 meters per second squared, 1.6 times 10 to the power of -5 feet per second squared, without invoking artificial origins. Key finding 2. Previous theories, ranging from Avi Loeb's provocative alien probe hypothesis to natural fragment models, highlight the object's elongated shape and reddish hue, consistent with cosmic ray exposure over millions of years. As detailed in NASA's 2025 comparative analyses with 3I Atlas, revealing shared hyperbolic velocities around 26 kilometers per second, 16 miles per second. Key finding 3. New evidence from 2025 studies, including dynamical ejections from giant planet systems, underscores Oumuamua as a relic of galactic formation processes, with supporting data from the Vera C. Rubin Observatory, indicating potential annual detections of 15 to 70 similar interstellar objects, transforming rarity into routine. Looking ahead, this suggests a burgeoning era of interstellar astronomy, where advanced telescopes like the Rubin Observatory could unveil a fleet of such visitors, enabling in-situ missions, perhaps intercepting one with a probe akin to NASA's Voyager journeys, but targeted at these nomadic intruders. Future trends may include refined models predicting object compositions, aiding planetary defense against potential impacts, and opening doors to sampling pristine materials from alien worlds. Beyond Oumuamua itself, this teaches us about the universal principle of cosmic connectivity. Our solar system is not an isolated island, but part of a vast galactic archipelago, where ejections from one star's nursery can seed discoveries in another's realm, echoing the interconnectedness seen in Earth's own geological migrations during the space age. Returning to our opening question, we now understand that Oumuamua's mysteries are largely unraveled through natural astrophysical processes. Yet its story leaves room for wonder, like an unfinished chapter in the grand narrative of the universe, inviting us to keep watching the skies.